So for our Be the Teacher project, we chose to do Chapter 1.2, Exponents and Radicals. So we're going to start off with a quick lesson on exponential notation. So a is any real number and n is a positive integer. Therefore, a to the power of n equals a times a times a, and then however many numbers n is. So in this case, n is the factor. The number a is called the base and n is called the exponent. So for example, negative 3 to the power of 4 can be multiplied out as negative 3 times negative 3 times negative 3 times negative 3 again. So that's going to be negative 3 times itself 4 times because that's how much the exponent is. And that's going to give us 81. And then we have another example, which is 1/2 to the 5th power is going to be 1/2 times 1/2 times 1/2 times 1/2 and times 1/2 again, which is then going to multiply out to 1/32. So on our second slide here, we've got another rule to follow. So when you have like bases and different exponents, you can combine them as we show right here. So for example, a to the power of m times a to the power of n can be simplified out as a to the power of m times n. Or to use real number examples, 5 to the power of 4 times 5 to the power of 2 can be simplified out as 5 to the power of 4 plus 2, which then equals 5 to the power of 6. Then we have a couple more rules underneath, so a to the power of 0 equals 1, and a to the power of negative n equals 1 over the power of a to the nth. So basically what this implies is that any number to the power of 0 is going to equal 1, and any number with a negative exponent is going to equal 1 over that number and its exponent in order to get rid of the negative. So for example, 4 over 7 to the power of 0 equals 1, because again, any number to the power of 0 is going to equal 1. And negative 2 to the power of negative 3 is going to be 1 over negative 2 to the third, because we want to get rid of that negative exponent, which is then going to give us 1 over negative 8, or just simply negative 1 over 8. And underneath we have the overruling standard of expression, which is going to be x to the negative 1 equals 1 over x to the first power equals 1 over x. So over here we have some laws of exponents. So on our left hand side are going to be all of our constant laws, and on the right hand side are going to be examples of a law. And if you ever want to pause and take notes during any point in the video, now would be a great time. On to our next lesson, which is going to be scientific notation. A positive number x is said to be written in scientific notation if it's expressed as followed. X equals a to the x times 10 to the nth power. So in this form, we see the scientific notation standard, which is going to be the x and the 10, where the a is going to be the constant and the n is going to represent the exponent. This follows the rule that 1 is less than or equal to a, which is then less than or equal to 10, and n is an integer. And then we have a couple examples. So we have 4x 10 to the 13th equals 4, and then however many zeros are in the exponent. So in this case, it's going to be 13. So if the exponent number is positive, that means that it's going to come before the decimal, and therefore it's going to be a larger whole number. Underneath, we see what happens if the exponent is negative. So in this case, 1.66x 10 to the negative 12th, where there are going to be 12 zeros, but in this case, because the exponent is negative, it's going to come after the decimal, which is going to make it a smaller number. So if you count, there's still 12 zeros in the second example and 13 zeros in the first example. So underneath, we have an example of what happens when you want to combine scientific notation. So we have 4.6x 10 to the negative 4th times 1.697 times 10 to the 22nd over 2.91 x 10 to the negative 18th. So what we're going to do is we're going to take all the base numbers. So we're going to take 4.6 from the first parentheses, 1.697 from the second, and the 2.91 from the denominator. And we're going to combine all of this into one fraction, which is going to be on the left side. Next, we're going to take the scientific notation format, so the x10, and then we're going to pull all the exponents from the stanzas that we had before. So then we have the negative 4 from the first parentheses, and the negative 18 from the bottom is going to be brought up, and that's going to be positive 18. So now we have negative 4 plus 18 plus 22 from the second parentheses, and that's going to give us 2.7x 10 to the 36. Radicals in the nth root. Square root of a equals b therefore implies that b squared equals a, and thus b must be greater than or equal to 0. Since a equals b squared must be greater than or equal to 0, the symbol square root of a makes sense only when a is greater than or equal to 0. For example, the square root of 9 equals 3 because 3 squared equals 9, and 3 must be greater than or equal to 0. The definition of the principal nth root of a is defined as follows. The nth root of a equals b therefore implies that b to the nth power equals a. So again, we have another slide full of properties. So on the left-hand side are going to be your properties, on the right-hand side are going to be examples. Once again, if you feel the need to pause and take notes, go ahead and do so. So now on to our final slide, which is going to be all about rationalizing the denominator. So we have our example problem over here, which is going to be 1 over the square root of a. Now we want to get rid of that square root on the denominator in order to make it a whole number. So what we're going to do is we're going to take 1 over the square root of a, multiply it by 1, which is then going to give us 1 over the square root of a times the square root of a over the square root of a. So what we did here is we took our original problem, which is 1 over the square root of a. We multiplied both the top and the bottom by the denominator, which is the square root of a, in order to get rid of that radical. So this is going to give us the square root of a because 1 times square root of a equals square root of a over a, because square root of a times square root of a equals a. And this follows the property that's underneath, which is the nth root of m times the nth root of n minus m equals the nth root of a, m plus n minus m, which then equals the nth root of a to the n, or just a. So then we have a couple example problems. So number 1 being 2 over the square root of 3 can be simplified down as 2 over the square root of 3 times the square root of 3 over the square root of 3. So once again, we just took that original problem and multiplied both the numerator and the denominator by the radical on the bottom, which then gave us 2 to the rad 3 over 3. In number 2, we have a little bit of a more complicated one with 1 over the cube root of x squared equals 1 over the cube root of x squared times the cube root of x squared over the cube root of x squared equals the cube root of x squared over the cube root of x to the third power, which is then going to give us the cubed root of x over x. In number 3, we have the 7th root of 1 over a squared equals 1 over the 7th root of a squared equals 1 over the 7th root of a squared times the 7th root of a to the 5th over the 7th root of a to the 5th equals the 7th root of a to the 5th over the 7th root of a to the 7th. And this is going to give you your final answer, the 7th root of a to the 5th over a. Thank you guys so much for watching our lesson on 1.2 rationals and exponents, and me and Amy wish you guys all good luck on the final.